Hello, today we're gonna talk about suspension component loads, and we will illustrate these ones with McPherson and SLA suspension types. We will start with the basics, some definitions, and we'll start with spring rate. Is the force needed to compress a spring certain distance? It depends on the constant of the spring. If the spring is very high, the force needed to compress it a little while, it's gonna be very strong. Then we're going to have the suspension rate. This is the force needed to compress the suspension system a certain distance. The system is R, the spring attached with the damper. Then we got the wheel rate. Wheel rate is the rate of spring acting at the tire contact patch, and it is the part where the spring and the wheel are together. So if the spring moves a little, the tire will move a little well also. Then we have the tire rate. This is the force required to vertically deflect the spindle location of a tire assembly towards the track surface. So is the force needed to compress the tire a little, and we have the formula that is K equal to max load over unloaded diameter by 2 minus the static max load radius. The max load is the load that can support a tire, and the loaded diameter is when the tire is without loading, and the static max load radius is when the car is moving and the tire has its normal radius. Then the ride rate is vertical force per unit vertical displacement of the tire ground contact with respect to the chassis. So is the force that acts in the springs and that is acting vertically to the perpendicular to the surface and compress the suspension a little. We'll talk about the McPherson, is the one of the two suspensions we're going to talk, and these are some of the parts we're going to explain. The upper arm. The upper arm is the part that allowed the spring and the knuckle to be together and to act as a single system. It's attached to the spring and supports the damper and the spring to get away from the suspension. There, the damper spring is the spring that absorbs all the energy, all the forces that acts vertically in the suspension. It depends its hardness of the constant. Then we have the stabilizer bar. It is attached to the chassis. It stabilizes the car when it's in a corner. Then we have the lower arm. The lower arm supports all the part of the suspension, supports the damper, the spring, and is connected directly to the chassis. It also has the stabilizing bar. Then the damper fork is the one that joins the damper with the lower arm. The drive shaft boot is a part made of rubber material and protects the joint from dirt and from hitting with rocks or something else. The radius rod is a suspension link that controls the wheel motion in the longitudinal direction and is connected to the chassis. This part does not allow that the wheel get out of its axis. Then the castle nut is the part that holds the ball joint and the ball joint boot in its place. It's only a nut. The knuckle is the essential part of the system. It connects the wheel with the upper arm and all of the suspension. It's the one that transmits all the forces to the suspension to absorb them. The ball joint is the part that connects the control arms to the steering knuckles. So it's an essential part of the suspension.
Now we're going to talk about the SLA system. First, I'm going to name all the components of the SLA system. We have the shock absorber, the upper control arm, the ball joint, the knuckle steering, the other ball joint, the lower control arm, and the coil spring. Also, we have the frame. Now, in a typical SLA system like the one shown, each wheel assembly is mounted on a spindle that is carried on a steering knuckle. The steering knuckle is supported on the upper and lower control arms by ball joints. The control arms, in turn, are mounted onto the frame or front structure of the car so that they can pivot at their inner ends. This means that the outer ends of the control arms, which are connected by the steering knuckle and wheel spindle, would move up and down as the car travels over rough pavement. At the same time, each front wheel can be turned left or right to provide steering control. The ball joints permit the combination of movements, the flexing of the assembly to absorb road shock and the pivoting of the steering knuckle. Spindle and wheel let to the driver steer the car. Because the pivot points and other points of the motion can vary as they move, these parts are usually equipped with grease fittings for regular lubrication. A coil spring may be mounted between the spring housing on the frame or the frame member and the upper control arm. Springs may also be mounted between the lower control arm and the frame. Mounting on the lower control arm is more common. On some vehicles, torsion bars are used in place of coil springs. In the SLA type system, shock absorbers mounted inside of coil springs provide a damping action.
So let's talk about the graphical method. Let me explain. This method shows us how to calculate a resultant of multiple force acting on a concurrent coplanar load condition. It's used to analyze different systems. To solve graphically, apply the head-to-toe assembly force as this. Place point 0 on the paper. Move the force number 1, then locate this point 0 at the end of the force number 1. Move force number 2 so that the end of the force number 2 is located at the tip of force number 1. Head of force 1 to toe of force 2. Draw the resultant from point 0 to tip of force number 2. First, we'll talk about the McPherson suspension. In this kind of configuration, we have two types of force applied on the wheel. First, we have the force applied by the flow weight on the car. In this vector, we include the force generated by the vibration of the system, or the dump that causes the roar. Then we have force generated by the movement of the car, talking about the turns and the centripetal force generated by turning in great velocity. If we sum the force, we will have a resultant force that corresponds to the total energy supported by the suspension. So if we put on a graph the loads that apply in a vertical or lateral way. SLA suspension. This kind of configuration has two supports for the suspension, the lower control arm and the upper control arm. Both of these form a triangle. This means that the movement of the systems will be more steady because the configuration allows a better movement around the axis. Another advantage is that this configuration distributes the loads in a uniform way. So, in the case of hard system vibration, for example, if the car falls in a deep bump on the road, the suspension will distribute the heat's vibration in a way that the driver feels the less as possible. This configuration is more expensive than the McPherson suspension, but it's better and it's great to put in a system. So, thank you for your attention, and I expect that you enjoyed this video.